Euclidean world is how
अब
you
इसमें कोई
measure
दूसरा
distance between 2 points. So if you
अब
have
कोई भी ज्वाइन
2
कर पाएगा कि एक बार
points,
चेक कर लो उसको।
and what is the distance between these 2 points?
हाँ
You can resolve
तो वो
it
लिंक जो आपने मुझे मेल
along
भेजी
4
है वो वाली
orthogonal
मेल भेज दूँ
directions,
सबको ना तो वो ज्वाइन हो जाएंगे।
and then use the Pythagoras theorem, dx
अच्छा
square
अच्छा
plus dy square equal to dz square. And in 3 dimensions, you can extend it.
अच्छा
So you have dx square plus dy square
अच्छा
plus
तो वो
dz
लिंक ठीक है
square.
तो फिर अब मैं वो लिंक जो है
dz
इसमें
square.
कॉपी करके सबको भेज देता हूँ
In
व्हाट्सएप कर देता हूँ।
general, the
ठीक है
law is
वो
given
ट्राई
by
करके
this. But notice that when
एक सेकंड
you
होल्ड करो
use
सर बस एक बार।
Euclidean geometry, you're using the plus sign everywhere.
हाँ ठीक है मैं एक बार
And
दूसरा
I
भेज
will
देता
not
हूँ।
go
ठीक है सर
into the mathematics of the space-time continuum, but to be able to understand the distance between two events, what is required to make the theory work is the recognition that we live in a world which is not just three-dimensional, but it's a space-time
नहीं
continuum.
आपको आपके वेबल
It is a four-dimensional world, but it is not a Euclidean four-dimensional. You can't just add one additional dimension to the previous one. You can go from one dimension to two-dimensional Euclidean space. You can go from two-dimensional to three-dimensional Euclidean space by simply having an orthogonal axis. But when you go into the space-time continuum, you should do that, but there is a sign manipulation in the what is called as the G matrix. Again, I will not go into the into the mathematics, but you have the G matrix of the special theory of relativity, which is flat, and then you have the G matrix of the general relativity, which is not flat because it belongs to the curved space-time continuum. This is flat, and this is curved space-time continuum, and it predicts gravitational waves. So this is this was these waves were actually detected, and the celebration at Jaipur today on the September 23 is an anniversary event. These were observed in a very long time, several months before the big wave studies right here in India, because the LIGO India gravitational wave detector we are building in our own country by the Department of Atomic Energy finding answers. But then I told Thomas that there is a second story that I'm
Can I? Am I audible? Am I audible? Can I start? I can't hear you. Hello, Lokesh ji. I think I have become the
Hello. Hello. I have become the host of this meeting. supposed to be giving a talk to the speaker. Hello, Dr. Sharma.
सर कोई सिफारिश लेके गए पर दिखा देना तो मैंने लिख के भेजा कि
आपकी आवाज बहुत ब्रेक हो रही है, ठीक है?
permitted to work. Yeah, good morning.
Hello.
Good morning.
Hi, good morning, good morning.
So we will start within 2 or 3 minutes.
Yes, yes, no issues, no issues.
So
Just one more thing.
you know that's a novel law. जब वो का नाम है से तो he was busy. Just slip what is it there? Was not the president that time. अगले 1 साल तक वो रोज सुबह 8 बजे उठते उठते ऑफिस में पहुंचते हैं और शाम को कहते आज जरा साफ करना यार ये काम करो एक दिन वो दोनों अकेले ही थे तो तुमने मुझे बताया कि नहीं वो पर्ची के पड़ गया और the whole 1 year पार्टी इसमें प्रेसिडेंट बना सिर्फ जो कहा सब्जी लाना फूड लाना मेरे कुत्ते को मार लाना सर was an authority that the president called him उनका नाम भूल गया तो फील्ड में वो अपने आप में बहुत बड़ी अथॉरिटी थे वो गाइड से थे वो तो नंबर पर तो इस तरह के लोगों से जो इंटरेक्शन मिलता है जो ज्ञान मिलता है जो आनंद आपको आता है वो आपको कोई जगह देगा आपकी अपने जीवन में ठीक है some other meeting where we can meet so please enjoy the day lunch break होगा फिर उसके बाद वापस आएंगे try to be here try to learn something then we will meet मैं तो बिजी रहूंगा सर लोकेश कमिंग है एक आपका इसके बाद एक गेस्ट होगा है ना ऑनलाइन लगे गेस्ट में और भी जो मैंने दिया था वो एक स्पेशल प्राइज अलग से ठीक है ओके बेटा बाय बाय थैंक यू So, ma'am, you can start, please.
I can start. Okay, all right. Hello, everyone. Good morning. So my name is Amrita Sadhu. I teach at St. Xavier's College in Mumbai. And today I'll talk to you about general relativity and gravitational waves. So the whole day's program is organized in the honor of for detecting the first gravitational waves, and since then we have detected a lot of them, right? So I'll give you a brief introductory talk on what these waves are and where these waves come from, right? So as we know, our general day-to-day life, things are in our day-to-day life, systems in our day-to-day life are hello.
Yeah, ma'am, you can continue.
All right. Sorry. Systems in our day-to-day life are described by Newton's laws of motion, right? And especially the first law says that an object either remains at rest or continues to move at a constant velocity unless acted upon by a force. Right? Now, okay, when we observe anything, right, it is from our point of view, and the name for that in physics is called a frame of reference. Right? The frame of reference in which this first law is obeyed is called an inertial frame of reference. Right? So actually, this frame of reference, it turns out, is not a unique frame of reference. Think of it this way: if there are two cars moving, right, one car is moving towards other, and there is a third person who's standing on the road, right? Each of the people will see that the car is moving at a uh, each person will see the motion of the car or the velocity of the car differently depending on which of them is looking at the system, right? So this is essentially, in the classical sense, what we call it that a principle of relativity, right? So what does the Galilean principle of relativity or Newtonian principle of relativity says? That the laws of motion are the same in all inertial frames of reference, right? Okay. Now, also you can think of this in the sense that maybe, if you move from, if you're standing here, right, or sitting wherever you are, if you change two benches and look at a ball moving, you're still going to see the same kind of motion, right? That law of motion doesn't change where you are sitting in the class, right? So this is basically the idea behind a principle of relativity. Okay? All the things that we observe are relative to one another, but excuse me, there's some disturbance from your side.
Which kind of disturbance we are okay from here?
Oh, I thought somebody else's mic is on. Oh, I think it is. I'm getting the feedback from your side to mine. One sec. Let me try and see if I remove my headphones, if the feedback gets better.
Me now? Could you please confirm if you can hear me?
Yes.
Okay. All right. So, Newton's laws are true in a frame of reference that is called inertial frame of reference, and that reference frame is basically any frame of reference that is in uniform, has a constant velocity with respect to one another. There is no absolute frame of reference, right? But in all of this, Newton makes a crucial assumption. And the assumption is that in each frame, the time that the person sees is not relative. There is some absolute time. My watch, your watch, somebody else's watch, all of the watches will show the same time. Okay. Now, this is our general, the Newton's laws of motion describe our universe in, say, in mechanics, how our cars move, how our physical things move, right? And how our planets move even. Correct. But so there are another set of motions, equations in physics, which are called Maxwell's equation. Now, we are all familiar with electricity and magnetism. I mean, that is essentially how we are able to have this lecture anyway, right? So, okay. So these various laws describing behavior of electricity and magnetism were experimentally and theoretically established, right? So some 200 years later, after Newton gave his laws of motion, Maxwell formulated the equations that describe the behavior of electromagnetic fields. Okay, so he combined the laws of electricity, magnetism, wrote 4 equations that describe all of the behavior of all of these like electricity and magnetic, systems. Okay, now these equations, when we combine in a certain way, give an equation that describes behavior of a wave, and that wave, it turns out, is light. Okay, uh, and more importantly, this combined equations, or the combined form of Maxwell's law, say that the light has a constant speed in vacuum. We call that c. Okay, and its value is somewhere around 3 into 10 raised to 8 meter per second. Now so now if we treat light as a moving particle, right, according to Newtonian relativity, the speed of light must be different in different inertial frames. If I am walking towards the light, I should see its speed different. If I am walking away from the light, I should see a different speed. But when we write Maxwell's equation, they do not allow for such a change in speed of light. But both of these theories are experimentally verified. We know Newton's laws are correct because that is our day-to-day life. We know Maxwell's equations are correct because that is also our day-to-day life experience, right? So if we accept both concepts are correct, then we have to accept that Maxwell's equation have some one preferred frame, which we call ether frame. Okay, we say that there is only one way to look at Maxwell's equation, and that is the only way we can look at it, and the speed of light is c in that frame. So Michelson and Morley tried to experimentally find the existence of ether. You will learn more about this experiment in the next couple of talks. But the result showed that no such frame exists, right? So now we still need to solve this problem, that both things are correct, but they are not agreeing with each other, right? So what we do is we that principle of relativity, how we write relation between two frames of reference, that is not we say that is not applicable to Maxwell's equation. Okay, so we can't the principle of relativity, which allows us to calculate speed of different things, that is not particularly, that way is not applicable when we look at Maxwell's equation. Okay, so in 1905, Albert Einstein proposed a special theory of relativity. Right? He said that the laws of physics are invariant in all inertial frames of reference. This is nothing but our old principle of Galilean relativity. But this, he put an extra constraint that the speed of light in vacuum is same for all observers, regardless of their motion of the light source or observer. And when you put these two ideas together, we get a new law of transformation between the two inertial frames. Okay, and this new law creates a new entity called space-time, right? And rather than having a three-dimensional world that we describe by x, y, z, right? So everything that we see has a height, a length, and a breadth. But we also have to consider another dimension, and that is time. And crucially, we should treat time the same way as we treat this space directions. Okay, so this is the new revelation brought by principle of special relativity. Okay, so the consequence of special relativity is they are far-reaching, right? They say that if you are moving, a moving rod will appear shorter for a person that is stationary. Okay. Similarly, a moving clock will run slower. Okay. So these are called length contraction and time dilation. Okay. And but we don't see these effects in our day-to-day life, right? So this theory reduces to our Newtonian mechanics for speeds that are much lower than speed of light. So our what we learn from Newton's law is correct, but if the moving object becomes very fast, nearly at the speed of light, then the Newton's laws are not correct. Then the special theory of relativity is correct. But there is a problem in this theory. And the problem in this theory is that this theory is only valid for things that are moving with a constant velocity. We cannot introduce acceleration in it. Okay. And there is no simple modification that we can do to special theory of relativity that will give us any acceleration, or specifically, we are concerned about gravity. It cannot, the special relativity cannot give us gravity. So Einstein realized that a new theory is needed. Okay. So then he did a thought experiment. He said, okay, I have a spacecraft that is, I have a rocket that is without windows. Okay. So if I'm standing on Earth, right? I can, this lady has a ball, she drops this ball, and on Earth, she will see it going down. Now, this rocket is accelerating upwards at a same rate as gravity, at 9.8 meter per second square. Okay. Now, when she leaves the ball, because it's in space, the ball doesn't move, but the rocket is going up. So this the ball so rather than ball touching the floor will go up and touch the ball, right? So but because this lady has no windows, so Einstein said that there is no way for her to figure out whether she is on Earth and ball is falling, or whether she is in space and the rocket is moving. Okay, so this is called a principle of equivalence. Okay? And from this principle of equivalence, Einstein proposed a general theory of relativity. He said that the local effects of motion in a curved spacetime are indistinguishable from those of an accelerated observer in flat spacetime. Basically, he said that you can't really distinguish between this scenario that you're on Earth and things are happening around you, or you're in a space-time, you are in a moving spacecraft, and you are the one that is moving, and things around you are not moving. Okay, so this theory, when we write its mathematical formulation, just like we have for Newton's laws, we have equations like F is equal to ma and so on. When we write equations for this theory, it says that the general theory of relativity says that the matter curves the space-time around it. What do we mean by that? Right? So look at this picture. There is, so we can imagine this space-time as being this sort of a background sheet that we are living in. Okay. And once we...
Sorry, ma'am, excuse me for sorry for interruption. Ma'am, please share your screen actually. So because we are not able to see your PPTs or.
Oh, okay. I have shared.
There is.
Okay, I see. One sec, one sec. I am also somehow the host of this meeting, so I keep getting this sharing keep stopping the moment I have to let someone in. So maybe that is how I got thrown out. Sorry. One sec. Oh, okay. All right. So the first few, this is not necessary, but okay. So this is the experiment that I was thought experiment that I was talking about. Now, can you see the picture? Okay. Uh, so see, this rocket is on Earth. The lady has dropped a ball and the ball is touching the floor, right? Now, this rocket is in space. The lady has dropped the ball, but now the ball is not moving, but the rocket is going up. So, what will happen eventually? This rocket will reach wherever the ball is, right? But to the lady inside, both the scene will look same. All she will see is that the ball is falling from her hand and touching the ground. Because there are no windows, she has no way to tell whether she's in this scenario or this scenario. Okay, so this is the principle of equivalence. Okay, and this principle of equivalence, Einstein gave in, sorry, 1907. Okay, and he says that the local effects of motion in a curved spacetime are indistinguishable from those in an accelerated observer in a flat spacetime. So, but the upshot of this theory, right, is that so okay, in easier language, what this also means that in a small enough region, we can use a special theory of relativity, right? But in a large region, we cannot use it. We need to we will have curvature of space-time. So we will experience gravity in a large enough space, and then that gravity actually is also due to, I mean, that gravity causes the uh, curvature of the space time. Okay, now so think of it like this. See, we all know that the earth is round, but when when we are sitting at a place or in our vicinity nearby, we say that we can see that the earth is flat. We don't consider the fact that earth is round. We treat it as a flat surface. So this is a bit like that. So on a larger scale, you have curvature, and in a smaller scale, you can treat your space-time, sorry, you can treat your space-time as flat. Okay, so, and this is a recurring theme in the general relativity. Okay, so this so it from there we can say that the matter or any star, when we say matter, we just mean like a very massive object, any star or galaxy or these celestial objects, they will curve the matter, curve the space-time around it. Okay, what do we mean by that? So imagine all of us living, uh, you know, uh, all the matter, everything we know is living on this sheet. Okay, and now when there is matter, so here when there is earth, this sheet is going down, it is getting curved. This is also like in your trampoline. right? You have a rubber sheet. If you keep something on it, the sheet will go down a bit because of the weight. So this is so this is something like that. And this fabric, this imaginary fabric is what we consider the what we think that the space-time would behave like. Okay, and so now, uh, because we are talking about curvature of the space-time, right? We have to consider, so we have to, what we are essentially saying is the sheet is bending, right? And now this, to characterize this bend, to understand this bend, we need geometry, okay? So this is the Einstein's equation of motion. Don't worry about what it is, but what is important is that the left hand side of the equation describes geometry of the space-time. It essentially measures how it is curved, and the right side hand side of the space of this equation describes how describes the matter that is causing this curvature. Okay, so this is in other words, a mass tells space-time how to curve, and a space-time tells mass how to move. Okay. All right. Now, there are some consequences to general relativity. And one of the most important consequence is that so gravity must affect light. Okay. So for the general relativity and the curvature of, because there is curvature of the space-time, the way light moves, right? It essentially loses energy as it goes from or it loses energy as it goes from surface of a planet to above. Okay, so and that we say is due to the effect of gravity. Okay, so this is something that we did not consider when we write our Newton's equation of motion. We don't consider gravity in them at all. Okay, so all right. So another consequence of this is that the path of shortest distance between two points is not a straight line, right? So if I tell you that, go somewhere, move from one space to another, what will you do? You will go in a straight line. If you have no obstacle, you will just go in a straight line, right? But because now imagine that the room that you're walking in, or the path that you're walking in, is say you're walking on a dome, or you're walking on a mountain, right? Then your path is from one place to another. The shortest path is not a straight line. You will have to go some curved way. So if you are a mountain, your straight line path will be go to the top and go down. But that is not the shortest route. You can take some other route that will be shorter. Correct? You can go by the sides, and that route will be shorter. So similarly, the path of shortest distance between 2 points is not a straight line, and the natural path of objects, and this includes even light, traveling in a curved space-time, is a curved path. Okay, thus we see bending of light around the stars or galaxies or any celestial object due to their gravity. Okay, what does that mean? That means that if there is something behind the star, so okay, okay, where is it? Is it moving? Yeah. So this means that so if there is a star behind our sun, because the light bends around it, the light that is coming from that star bends around the sun, we will be able to see that star even if it is behind the sun. Okay, and this is actually one of the tests of general relativity. Like, this was actually observed in 1919, and this is how we said that, oh, okay, this strange theory which asks us to do a lot of complicated mathematics is true. Okay. The other thing that it says is that the parallel lines on a curved spacetime need not remain parallel, and this we can see even in our usual day-to-day life, right? So longitudes on our Earth, right? At any given point in a small space, the longitudes are parallel lines, but you can have so if you keep walking along those longitudes, as we go to poles, right, the distance between them becomes shorter and shorter. So and at North Pole the two lines meet, but they were parallel at some time, right? In our school though, we have learned that, well, in our Euclidean so the usual three space that we work in, if there are parallel lines, they remain parallel throughout. So that is not true on a curved spacetime, right? So that also means if there are, say, two cars moving on a curved spacetime, at some point they will have an accident. Okay. Uh, so another useful, I mean, so again, this is you may say that, okay, but all of this is clearly not useful because my day-to-day life is still given by our Newton's laws of motion. But that is also not true, right? Because general relativity, uh, or rather our GPSs work because we have general relativity. So if you have a clock, so suppose there is a satellite, you have a clock and a satellite has a clock. Now, because the space-time, so because Earth has a mass, the space-time around it is curved, right? And now that because again we are dealing with a space-time, the clock from that is on Earth and the clock that is in the space in the satellite will run at a different time. They will not show you the same time, right? Now, but if you, in your GPS system, you want the clock to work at the same time, that GPS system is telling you where you are going and how you are going, right? If it falls behind, then you can't, I mean, you will be lost, right? But if you incorporate the answers given by general relativity, you can maintain the correct distance and correct time between you and the satellite, and you can go where, and your GPS will tell you your correct directions. Okay, so general relativity is also useful in day-to-day life. Okay, now so as we said that the general relativity gives some predictable gives some predictions, right? And these predictions are tested. They were tested in 1900s. Okay, so one of the prediction was deflection of light by sun, and that was done in Eddington. And he saw that these stars that we see, they should be behind the sun. But we are so when there is an eclipse, we need to do this experiment at eclipse, because otherwise the light from the sun is so much that you cannot see behind it. But during an eclipse, the light of the sun is blocked and you get a dark sky again, and you see some stars in the sky that should not be there. They're behind the sun, but you can still see them because the light from those has bended around the sun. Okay. Okay. Now, other testable prediction is that precession of Mercury. Okay. Now, the planet Mercury doesn't go the doesn't travel the same orbit each time. So centuries of observations told us that the point that is closest to the sun for Mercury, that keeps shifting at a very slow rate in a century, but there is a definite shift. Okay, and this shift was not uh, uh, this shift could not be predicted by Newton's laws of motion. But when we calculate this path of Mercury using the fact that sun is a massive body and the space-time is curved, right? We can find that we can find this correction. It is a very small and easy calculation, and we can match the prediction from the theory to the observed observed change in the location of this perihelion. Okay. Now, and this again we talked that so the frequency of a light that is sent from a surface to the to upwards changes, and the light there is so if you send out blue light, it will become redder. Okay. So these are the predictions, and these predictions were at various points were actually very accurately measured by people. Okay. Alright. So we know that general relativity is a good theory. Okay? And it predicts things that we can be tested. So since it's predicting some some day-to-day some measurable things, the question is, are there predictions in general theory of relativity that are not so obvious, that are not some nearby things that we can measure? Right. So one of the most exotic things that the general theory of relativity predicts is existence of a black hole. Now, black holes are essentially dead stars. Okay, they're formed by very massive dying stars, and those stars essentially they become so heavy that they collapse on themselves. Okay, and their gravity becomes so strong that the light cannot escape from them. Okay? So black holes are these regions of space-time where gravity is so strong that even light cannot escape. Now, because their gravity is so strong, the curvature in near the curvature of the space-time near the black hole is so high that they form a boundary, and this boundary is called an event horizon. It is called a horizon because anything that travels beyond this event horizon into the black hole cannot come out. It's one-way door. You go in, and that is it. You cannot come out of it, right? This initially when these objects were predicted, people didn't believe them, but a lot of work by like Chandrasekhar and other people, right? And so there is Penrose, Stephen Hawking, and so on. And then black hole became like an accepted so an accepted solution to the equations of general relativity.
Hello.
Yes.
Hello.
Yeah.
Amrita,
Huh?
can we conclude now, please?
Oh, can you give me 2 minutes?
Yeah,
5.
please. Okay.
Yeah, all right. Okay. So, okay. Now, but now the existence of black holes has been validated by various observations. Okay. All right. So this is the latest observation of black hole. this is actually, this is not how it looks like, but think of it like we have painted it this way. Okay. Now, another thing which today's program is about is another thing that these equations predict is the is the gravitational waves. So suppose you have a pond, right? And you throw a rock in it. It creates wave, right? So similarly, so if you have a moving mass, an accelerating mass, the gravitational, so this space-time in which this mass is moving will create ripples. Okay, and these ripples are called gravitational waves, and these were predicted in 1916 by Einstein. Okay, these ripples, the strongest gravitational waves are formed by most violent events, which is colliding of two black holes. Okay, and these cosmic ripples would travel at the speed of light, carrying with them information about where they came from, how they generated, and the nature of gravity itself. So, indirect detection of gravitational waves was done by Hulse and Taylor in 1974. They looked at two very heavy pulsars. They are sort of dead stars moving around each other, and they found that that their orbit, the rate at which they are getting closer together was only made sense if you consider that they are losing energy in gravitational waves. And these people got a Nobel Prize in 1993 for that. But the event that we are celebrating, the direct detection of gravitational waves from merger of two black holes, this detection was done on 14 September 2015 by LIGO. They detected these waves. How they detected will come in the next talks, right? But they detected these the oscillations in the space-time caused by gravitational waves of two generated by two colliding black holes 1.3 billion light years away. And this is how the prediction, so okay, this is how the predicted waveform looks like, how the predicted wave looks like, and this is what they observed. So pretty close, right? So one second. Okay, this is not running. I just want to run this simulation and then I'm done. Yeah, okay. So see, now there are these two very massive stars, and this is how they are creating ripples in the space-time. And as they are getting closer, the ripples are coming faster, and they're also increasing. Their amplitude is also increasing, right? And when they sort of collide together, we get a very violent event and very waves of very high intensity. And as the two colliding black holes form together, they will eventually lose all their energy by these collisions, by the gravitational waves, and become one final star. Okay? So this is the event that we essentially looked at. Okay. So why do we bother with all this? Well, one, because it tells us about how the nature that we live in, the universe that we live in works. And even though we like general theory of relativity, it still leaves some unanswered question for us. So we hope that looking at gravitational waves will tell us more about those unanswered questions, right? So, okay, so this is why we should bother with these things. And this year, a detector has been sanctioned in our country and it will be built in, I guess, some years. So you can also participate in this endeavor. All right. Thank you for listening. If there are any questions.
Yeah, Amrita, very good, very nice talk. Thank you very much for elaborating the things very nicely to our students. Yeah, so students, if you have any questions, Lokesh sir, could you help us? If they have any, please write it down and we can convey it to ma'am, and then later on we can get and discuss this, the answers which she will be giving about those queries, right? Yeah. Amrita ji, if Professor Shinde is still your principal,
Yes, yes.
please say my hello to him. He's a good friend of mine.
I
We are
see.
together. Yeah.
I'm sorry, I don't know your name.
Yogesh, Professor Yogesh Chandra Sharma.
I see, I see.
Yeah.
I
So
will
we are very thankful to the speaker as well as the national executive member in IAPT from Rajasthan, Professor R.K. Khanna, who is there to bless us. Sir, आप 2 मिनट कुछ बच्चों को गाइडेंस देना चाहें 2 मिनट के लिए, हालांकि आपका लेक्चर है बाद में शेड्यूल्ड, आपकी ब्लेसिंग्स मिले.
Is it? I am
Yeah.
audible.
Yes sir, you are audible.
Very interesting lecture. I enjoyed it, and I hope the student also might have enjoyed it, because it is a difficult topic. Gravitational wave itself is a
yes.
scientific field in all, and lot of things to be learned by every one of us, including the experts.
True.
And my question is that once we in the LIGO, we find the presence of gravitational wave, but is there any other way of validation of this result? How can we validate the result of LIGO?
Okay, so the way we validate is by so within LIGO itself, the result is validated by a lot of other. I mean, they have 2 or 3 detectors. They are measuring the same thing with a 2-3 instruments.
Yes,
so if
exactly,
all the instruments give same, then it is validated. Now, so this is a bit advanced, but if you have, say, a black hole and a neutron star colliding, right? So 2 black holes colliding will only give gravitational waves, but a black hole and a neutron star colliding will give you electromagnetic waves, especially in X-ray. Right. So if you simultaneously measure, gravitational waves in your LIGO type detectors, and at the same time you measure, this total influx of X-ray, some very bright event happening in X-ray at the same place or around the same place in the sky, then you know that, okay, these 2 are connected. So that adds another verification to your result, and that also has been observed.
Yeah, moreover, Amrita, what you were telling, actually, Professor Khanna, the photo you have shared with us, even there are 2 LIGOs at 3,000 kilometers away from each other, and one is at in Europe. So those 3 detectors, they are detecting the same event. So that has been validated like that. And after that, after that,
Yes.
after that only it was declared that yes, we could detect gravitational waves like that.
No, that is true. But the question is, because that event happens once in a lifetime.
Yeah.
No, they've been observing things like that for it turns out that there are a lot more black holes in the sky than we predicted.
That's
Sir,
what I'm
sir,
saying.
sir, sir,
So
sir,
they have, I
सुनिए
think,
सर.
now 50 events, something like that.
सर मैं बताऊं सर, इसमें क्या है, वो बिग बैंग के बाद जो भी इंसिडेंसेस हुए थे, उनका लगातार इस तरह के जो भी इंसिडेंसेस हैं वो डिटेक्ट होते रहते हैं वहां पर फॉर द टाइम बीइंग और इंटरवल. We will discuss it later on. So I think it is high time we should break for half an hour. Students will meet at around 1:30 and we will have the further lectures after this particular break. Thank you very
I
much.
will, thank you. I
Yeah.
will not be able to join because
Okay.
I have lecture now.
Okay,
So
okay. Thank
thank
you.
you.
Please ask Shinde sir that I was telling.
Definitely.
Yeah.
Uh,
Thank
Okay,
you.
खन्ना सर,
Thank
मिलते हैं
you.
ब्रेक के बाद. Thank
हाँ,
you. Okay,
ठीक.
bye bye everyone. लोकेश जी लॉग आउट मत करिएगा, है ना लोकेश जी, अदरवाइज ये मीटिंग एंड हो जाएगी. कीप इट कंटिन्यू. ठीक है.
Yes, sir. Yes, sir. So are we starting now, sir? Okay. Yeah, okay, okay. No, he mentioned we will start at 1:15. So, okay, okay, okay. So how long would it take, sir? Oh my God. Okay, 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 sir. Okay, good afternoon, everyone. Post-lunch session. I'll keep it very brief, and I'm going to talk today on revelations of celestial ripples. Basically, I'm going to focus on an introduction to gravitational waves, what is general theory of relativity, how gravitational waves helped, you know, to verify the general theory of relativity, and uh, a couple of slides on how we can correlate gravitational waves with electromagnetic symphony. Well, I am Anirban Gupta. I am working in the Department of Physics, School of Basic and Applied Sciences, Faculty of Science and Technology at the JSPM University, Pune. And I thank again Dr. Yogendra Sharma sir and all the organizers for giving me an opportunity to speak during the second national seminar on discovery and detection of gravitational waves, which is held at Jaipur National University in association with IUPT RC6. So, brief introduction. The existence of Okay, and again, so the existence of gravitational radiation is a natural prediction of any relativistic description of the gravitational interaction. Gravitational waves were introduced basically as solutions of the linearized Einstein equation around at space-time. We'll be discussing more on this. These waves are shown to propagate at the speed of light, and they possess two polarization states. Now, this particularly has come is from the tensor part, where you have two polarization states of the gravitational waves, which are basically denoted by H plus and H cross. So, okay, we'll not go into details of that, but yes, please remember that. Please note that gravitational waves do have two polarization states. Gravitational waves can interact with matter, allowing for their direct detection by means of laser interferometers. Phenomenon that is now used, a principle that is now used in the detection of gravitational waves adopted by LIGO, right, which was introduced in 2015. Together with black holes and the expansion of the universe, the existence of gravitational radiation is one of the key predictions of Einstein's general theory of relativity. So, now, what are gravitational waves? Gravitational waves are basically ripples in the space. So, if you have a fabric and you drop a heavy object in the center of the fabric, you would observe some ripples, right? So, these ripples are basically something which is analogous to gravitational waves. So gravitational waves are ripples in the space-time, which we generally call as the fabled fabric of the universe. And it is caused by massive objects moving with extreme accelerations. And these are some of the most violent and energetic processes in the universe. So in the outer space, objects like neutron stars or black holes orbiting around each other at ever increasing rates, or stars that blow themselves up, they all give rise to gravitational waves. Now, how does this general theory of relativity work? Albert Einstein, back in 1916, predicted in his general theory of relativity the existence of gravitational waves. And what was the prediction? Einstein mathematically Einstein's mathematics, he mathematically showed that massive accelerating objects would disrupt space-time in a way that waves of undulating space-time were propagate in all directions away from the source. So the cosmic ripples would travel at the speed of light, carrying with them information about their origins as well as clues to the nature of gravity itself. So here you can see an image which was a two-dimensional illustration of how mass of the universe distorts space-time. So you have this space-time and you have Earth, which is shown in the center. And imagine that it's a fabric and you drop Earth on it. What would the shape the fabric would take? There would be ripples seen, and these ripples are analogous to water gravitational waves, basically. So according to general theory of relativity, what Einstein wrote in his book on general theory of relativity, he said that a pair of black holes orbiting around each other lose energy through the emission of gravitational waves, just like in photoelectric effect, how would an electron lose its energy? It would give out a photon. Okay, and in lasers, suppose an electron transition from the higher energy level to lower energy gives out a photon. So here, the black holes which are orbiting around each other, they would lose energy in the form of not electromagnetic but gravitational waves, causing them to gradually approach each other because their energies are decreasing. They would approach each other and then much more quickly in the final minutes. So during the final fraction of a second, the two black holes would collide. Okay, they would collide at nearly one half the speed of light and form single more massive black hole, converting a portion of the combined black hole mass to energy. Now, this was Einstein's mass energy relation equal to mc square. This energy is emitted as a final strong burst of gravitational waves. So, Einstein basically realized that massive objects caused a distortion in space-time.
Excuse me, sir. Sir, please share your PPT, because we are not able to see any PPT.
Oh yes, I'll do that. So please see if the PPT is visible now.
Yeah, good afternoon. Hello. Dr. Anirvan.
Good afternoon, sir.
Yeah, how are you? Fine?
Sir, I'm good. Thank you so much.
Yeah. So can
Yeah,
we
yes.
can we start?
Yes, sir, please.
You please start.
Okay, am I audible, sir? Am I
Yeah,
clear?
yeah, you are audible and clear. Please.
Okay, that's great. So could you please once confirm if the slide transitions is working?
Yes, yes, they are working.
Okay, okay, that's
Yeah,
great.
please note down that we have to finish it by 20 minutes, right? Okay,
I'm
sir.
sure I'll do that.
Okay,
Okay.
sir. Thank you, sir.
Shall I start? Shall I begin, sir?
Yeah, yeah, please.
Okay, okay. So good afternoon, everyone. Uh, Welcome again on behalf of the organizing committee, and I would like to thank uh, Professor Dr. Yogendra Sharma sir for giving me this opportunity to speak during the second national seminar on discovery and detection of gravitational waves, which is organized by the Jaipur National University in association with IIPTRC 6. Well, I'm going to speak on the revelations of the celestial ripples. Basically, the gravitational waves. I'm going to introduce what are gravitational waves, some brief introduction to what is general theory of relativity, and at the end, for a couple of slides, I would just correlate how gravitational waves and electromagnetic waves are different. So I would be speaking on this electromagnetic symphony. Well, I am Anirvan Gupta. I am working in the School of Basic and Applied Sciences, Faculty of Science and Technology at JSPM University, Pune. Well, so a brief introduction to what we are going to discuss. We are going to discuss the existence of gravitational waves. So, existence of gravitational radiation is basically a natural prediction of any relativistic description of the gravitational interaction. So, gravitational waves were introduced basically mathematically as solutions of linearized Einstein equation around something known as space-time. So these waves were proved that they travel with the speed of light and they possess two polarization states. Now, this is a really difficult thing to imagine how gravitational waves would have two polarization states, but it again has to do something with this tensor calculus, tensor analysis basically, wherein it is proved mathematically that it has two polarization states given by H plus and H cross. So gravitational waves can actually interact with matter and we can actually have their direct detection by means of laser interferometers. Problem I think. Just give me 1 second. Oh, yes. So gravitational waves can actually interact with matter. So we can have their direct detection by means of laser interferometer. So this principle is very widely used now in this LIGO, which was set up very recently. So together with the black holes and the expansion of the universe, the gravitational waves, the existence of this gravitational radiation or gravitational waves is was one of the key predictions of Einstein's general theory of relativity. So what are basically gravitational waves? Gravitational waves are the ripples in space-time. We call it in general the fabric of the universe, which is caused by massive objects moving with extreme accelerations. So these are basically some of the most violent and energetic processes which are happening in the universe around us. So in outer space, if you're talking about outer space, this would basically means all these neutron stars or so as to say the black holes. They would orbit around each other, they would collide with each other, and the result would be a massive black hole, which and along with some gravitational waves which are emitted. So an image is shown, which was generated by NASA. So how does the general relativity work? Albert Einstein back in 1916 predicted, basically he mathematically showed that massive accelerating objects, for example, these black holes, they would disrupt space-time in such a way that the waves of undulating space-time would propagate in all directions away from the source. So adjacent, there is an image which is shown, and you can imagine that there is a fabric, and suppose Earth as a massive object falls in that fabric. Then what would happen? How that fabric would look like, and how these ripples on this fabric would look like. So this is analogous to something, the gravitational waves which are moving out when these massive objects are actually treated in space-time. So this was Albert Einstein's, prediction, and according to general theory of relativity, he said that a pair of black holes which are moving around each other, they would actually gradually they would approach each other over a billions of years. So it's a long time that would take, and then when they come close to each other, they would move close to each other much more quickly, and when they move close to each other, they would nearly travel with one half of the speed of light, and they would collide with each other, they would fall into each other, and they would create a single more massive black hole. So this black hole, what happens, a portion of the combined black hole's mass is converted to energy, which was then given by Einstein's mass energy equivalency equal to mc square. So this energy is finally emitted as the gravitational waves. So we call it as the final strong burst of gravitational waves. So these are the ways which our LIGO has now observed. I'm sure someone else would be speaking on LIGO, how LIGO works. Okay. So starting with Newton's law, how do we come up to general theory of relativity? So Einstein realized that massive objects cause a distortion in the space-time. So if you imagine, that is what we said in the previous slide, if you imagine a large object in the center of a trampoline, what would happen? So object would press down into the fabric, and ultimately causing, there would be some dimple, there would be some fall in the fabric. So if you then attempt to roll a marble, suppose I leave a marble, you have a fabric, you drop a heavy object, massive object in the center of the fabric, and then at the edge of the fabric, I leave a marble. Then how that marble would, make a spiral round, and it would fall into the, trampoline, at the center of the trampoline. So this is the same way that gravity actually pulls everything in space. So that is what is basically happened. This is analogy. So there was an analogy which was given by Francis Everett from Stanford University, and he said that imagine that Earth were immersed in honey. So if you try to pull out what kind of ripples you get in honey, those ripples are analogous to what you actually see as gravitational waves. So adjacent is an image by NASA's Gravity Probe B, GPB. Okay. So how gravitational waves are produced? The strongest gravitational waves are produced by cataclysmic events, such as this collision of black holes or supernovae, which are basically the massive stars which are exploding at the end of their lifetimes. or the neutron stars which are colliding. So other waves are predicted to be caused by the rotation of neutron stars that are not perfect spheres and possibly even the remnants of the gravitational radiation created by the Big Bang. So if we have an animated video, suppose I will play a video here. This is just an animation. Suppose two neutron stars are coming close to each other over a period of years and at the end they are colliding. So what kind of, waves they would emit? So this is a simple animated video. So when they come close to each other, they would move around even with higher speeds. Their speed would increase and ultimately they would form a massive black hole. And whatever we see around that, those are actually those gravitational waves we are talking about. Okay, and ultimately a massive object will be formed. So various other definitions of gravitational waves. What are gravitational waves? So these are gravitational waves that we speak about: a trampoline, a heavy object falling in, a marble, whirling around it. So whatever we see, those are in the form of gravitational waves. And John W. Wheeler made a comment that space tells matter how to move. So space will tell this matter how do you move, and matter will tell space how to curve. So if you put this heavy object on a trampoline, this heavy object would decide how the space will curve. This trampoline would curve. So space will tell matter how you have to move, and matter will tell space how you have to curve. So change in matter distribution will be equal to change in curvature, and propagating change in curvature will be the gravitational waves that we are talking about, which we get at the end. So if you talk about how gravitational waves are expressed mathematically, we generally measure gravitational waves as strain, which is formed. So it will be strain, right? A heavy object dropping in. So there will be some strain which is created. So basically, this is the mathematics. We are not going into details of that, however. So gravitational wave measure of its effect, specifically the ratio by which lengths are stretched or compressed, which is a dimensionless number. So you actually measure how these lengths are stretched or how these lengths are compressed. Okay. So that is where your tensor again comes in into picture. How do they have two polarization states that is related to this. So H given by delta L upon 2L. So delta L, which is 2D of the earth, 10 to minus 21, that is 10 to minus 14. So gravitational waves, therefore, very weakly they interact with matter, unlike any electromagnetic radiations. So what is this gravitational amplitude? Again, this H, which we defined earlier, it is given by 2 integral g dash dt square. I think we will not go into the mathematics as of now, but g dash is basically the physically measurable part of this gravitational wave. Okay. So in 1974, Russell Hulse and Joseph Taylor, they discovered a new pulsar. I have given a YouTube link here at the center of the slide. We can always, I would request all of you to please go through this link. So what was this new pulsar that was given? So basically that was where, and they received Nobel Prize for this. So the milestones were like in 1916, Einstein predicted the existence of gravitational waves. Around 6 decades later, in 1974, Russell and Taylor they discovered this binary pulsar. Okay, they discovered this binary pulsar, and again 4 decades later, many pulsar radio emission study was indirectly or mathematically done. So in 2015, we had LIGO discovered. So it took almost 60 and 40, that is, 100 years time from Einstein's prediction to actually observing gravitational waves. So that was the timeline, and this was a milestone actually. So how does this gravitational waves relate to electromagnetic waves, or rather, what is the difference between these two? This is a point to note. So electromagnetic waves are, although gravitational waves and electromagnetic waves, they share some similarities. They also differ strongly in their very nature and their main characteristics. So while electromagnetic waves are nothing but oscillations in the electromagnetic field that propagate in space-time, gravitational waves, as was predicted by Einstein's theory of relativity, are tiny propagating ripples in the curvature of space-time itself. So you have very tiny propagating ripples. So you have ripples which are generated and they move about. They move about with the speed of, almost at the speed of light, and they are the ripples in this curvature of space-time. Electromagnetic radiation is produced by the motion of a large number of microscopic charges, giving rise to an incoherent superposition of waves with a dipolar structure in the wave zone. Remember, electromagnetic waves, they are more related to dipolar structure. Because the wavelengths of electromagnetic waves are typically much smaller than the size of their sources, these waves can be used to produce images. So you have the visual front. In electromagnetic waves, we generally deal with the visual aspects. So gravitational radiations, on the other hand, is produced by the bulk motion of macroscopic masses. So you have heavy bulk masses giving rise to a coherent superposition of waves with a quadrupolar structure in the wave zone. So electromagnetic waves are more related to this dipolar structure, and gravitational waves are more related to this quadrupolar structure. So since the wavelengths of the gravitational waves are typically larger than their sources, the wavelengths of gravitational waves are larger than their sources, these waves cannot be used to produce these images. Rather, we are generally using gravitational waves for akin to stereo sound, you can say, the audible sound, right? So electromagnetic waves, they interact strongly with matter and are typically scattered many times as they propagate away from the sources. Gravitational waves, however, they rarely interact with matter and propagate almost freely in the universe, thus making their detection quite challenging. And therefore, from the Einstein's prediction to the actual detection of gravitational waves, it took 100 years, almost 100 years. So, however, the typical frequency is low enough, and therefore the amplitude of the wave itself, which decays like the inverse distance, can be tracked in time. Okay, so amplitude of these gravitational waves, they decay almost with the inverse distance, and therefore we are able to track them in time. So if I tabulate this comparison, what we can say, the electromagnetic waves with the gravitational waves, how do you compare? The nature of the electromagnetic waves, it is generally given in terms of electromagnetic field, and the nature of gravitational waves, it is generally given in the term of space-time curvature. What are the sources? For electromagnetic sources, they are generally the accelerated charges. For gravitational waves, they are the huge masses, the bulk masses, which are moving with a very high acceleration. Wavelength of electromagnetic waves, they are very small as compared to the source, size of the source. And in gravitational waves, generally the wavelengths are greater than the size of the sources, or at least comparable. The structure of electromagnetic waves, they are more dipolar. The structure of gravitational waves, they are more quadrupolar. The coherence is low in case of electromagnetic, high in case of gravitational waves. The interactions, electromagnetic waves, they interact strongly. The gravitational waves, they interact very weakly. The detection of electromagnetic waves is generally related to the power of electromagnetic waves. In gravitational waves, it is more related to the amplitude of gravitational waves. And analogy, as we mentioned, electromagnetic waves are more related to images, and gravitational waves are more related to the sound. That is the audition or vibratory, basically. So moving towards reality, I'm so sorry. Moving towards reality, what was actually done in 1993, Russell and Taylor, they received the Nobel Prize for their discovery of the binary pair of neutrons, which they did in 1974. And these neutron stars were 21,000 light years from Earth, their distance. 7 years later, 7 years later, after tracking the radio emissions of one pair of stars, Taylor and two other colleagues, Wisberg and Fowler, they noted that the time it takes for two stars to orbit each other was decreasing exactly in a way that general relativity actually predicted, that if two stars were radiating gravitational waves. More than 40 years later, in September 14th, the day that we are celebrating today, September 14th, 2015, gravitational waves were directly detected by LIGO's interferometers. So, how faint are these whispers? The LIGO, it's beautiful even to, appreciate this. LIGO must detect a change in arm length of about 10 raised to minus 19 meter, which is 10,000 times smaller than a proton. So achieving this degree of sensitivity is really credible. It's amazing, right? So there are advanced optical methods, advanced mechanical systems which are working behind the success of LIGO. And generally, there was a question from one of my students, so I mean, including this, are gravitational waves destructive? So the answer is the amount of space-time wobbling that gravitational waves generates or creates is approximately 1000 times smaller than the nucleus of an atom, and therefore gravitational waves cannot be destructive, right? You cannot use for destructive reasons. Well, I believe I have completed it in a hurry. I am occupied elsewhere at 2 o'clock. So these are the few important references that I have gone through. The first one is the theory of gravitational waves, which was one chapter that I have read, and rest were a few commendable theories which were given in some references. So that's all from my side, and thank you. I believe, Yogesh sir, if there are some questions or some suggestions, some comments. Hello. Sir, am I audible? Hello. Yeah.
Is there any question from outside students? सबको सब पता है.
I hope, sir, I have followed the timeline.
Hello.
Yes,
Hello. Am I
Yes.
audible?
Sir, you are audible.
Okay. Thank you, Dr. Anirvan, for a very nice talk. So students are listening to you very eagerly, and they are noting down if they have the queries. So Lokesh ji, could you call who is the next speaker? Dr. Geeta?
Yes, sir.
Yeah, Geeta ji. Meanwhile, our national president, Professor P.K. Ahluwalia sir, is there. Sir, could you? Hello. We will like to have blessings from you, sir.
Am I audible?
Yes, sir, you are audible.
Good afternoon, Ahluwalia sir.
Namaskar, namaskar, and thank you very much for giving me an opportunity to talk to you. I'm really very, very excited to be part of this. In fact, earlier also I joined, and this is a wonderful program which is going on. I think ever since we have been able to connect through these meets, this is WebEx meet, but any meet through which we have been able to connect, they are just wonderful ways of reaching out to people and giving them a wonderful exposure of the frontiers, particularly this seminar, which is focused on gravitational waves. That has given a lot of excitement in the last, say, I would, but a seminar of this magnitude on IAPT forum is in fact very, very welcome. And I can see Professor Gupta's presentation on the screen. And here also, he has talked about, I think, the possibility of the kind of ripples which we are now able to detect. India is very much part of that now under that LEGO project. And I think this is a wonderful opportunity for the students also to see what is happening in the frontier areas of physics.
Yes.
Earlier, we were focusing mainly on schools, mostly on demos, etc. But these platforms have added new dimensions for bringing new topics in the mainstream, areas, particularly for teachers and students at undergraduate level and postgraduate level. I must congratulate the organizers for such an imaginative program. I can see there are many other people also. Dr. Shyamkant Anwane is also there. He is one of the very prominent members of IAPT and is a wonderful speaker. Professor Anirvan's program, though I listened to it at the end only, but I could see from the title of your talk itself that how interesting it must have been. And fortunately, these talks are available to us later as well. So it is not that this talk is just finished. I think it is there for the people to view and appreciate and acknowledge also. On behalf of IAPT, I really thank all the participants and the resource persons without whom this seminar would have meant nothing. I can see Professor Venkatesh also in it. I can see Dr. Geeta also here. Professor Rajendra Kumar Khanna ji is also there. I'm very happy that very senior members of IAPT are also present in this. And I'm sure that as and when we will invite resource persons of this particular program to have some other such focused set of lectures, they will come forward and reach out to a very large community of about 10,000 members of IAPT. We are a very, very big community of teachers and students. And if any of you are not part of IAPT, I'll request both students and teachers to become part of IAPT. Students can become part of IAPT with a very nominal yearly subscription. And they will find that they will get exposed to very many resources which are available on our website, and many experts who can mentor you on very many other activities also. They can help as mentors for your projects. I think NEP is bringing out all such innovations in the curriculum. You require people from outside your institutions also to come and interact with you. And when you come here, you meet people who are actually working in these areas. And they are always, very, very happy to interact with students. So once again, I congratulate the whole team, Professor Vaisi Sharma, and your university. You do wonderful work for physics. Thank you very much.
Thank you very much, sir, for your kind blessings. Now I request the next speaker, Dr. Geeta Nair, to continue. Dr. Geeta,
Yeah,
am
good
I audible
afternoon.
to you?
Good afternoon.
Lokeshji,
Am I
Lokeshji,
audible?
you, yeah, Lokeshji, please take care. Yeah, please continue.
Shall I share my screen?
Yes, ma'am, please do.
Is the screen visible?
Yes, it is visible, ma'am. Wonderful title.
At the outset, let me thank the organizers for the opportunity. I'm going to speak upon the most famous failed experiment and its successful legacy. We all have a basic understanding of waves, and after the lecture by Sir on gravitational waves, I'm taking you slightly back in time to the beginning of, say, the 19th century. So we have seen water waves, sound waves, waves on a string, and we all know that all these waves are disturbances traveling through some medium. And by the 19th century, people had the idea that light is a wave. So it was natural to assume that it requires a medium to propagate. So the question was, if light is an electromagnetic wave, what is the medium of electromagnetic waves? So this was a question which was in the minds of scientific community by the 19th century. In 1860, Maxwell's equation had determined that light travels with the speed c. Since it was inconceivable to imagine that waves moving through empty space without a medium, people thought that there should be a medium that fills out the entire space, and they called it as ether or luminiferous ether. It was some medium which was invisible, but it filled all space and transmitted the electromagnetic vibration. On top of it, ether was given some unusual properties, like it was weightless, transparent, frictionless, undetectable, chemically or physically. We are not able to see it. And it is something which is literally permeating all matter in space. It had zero density and it is a perfectly transparent material. So the speed of light or electromagnetic waves was calculated to be 3 into 10 raised to 8 meter per second at this stage. So it was assumed that there is a unique frame of reference which was attached to ether, and the speed of light is c with respect to this frame. So there was a growing interest and need to experimentally verify whether such a frame of reference, which is an absolute frame of reference, exists or not. So what was the obvious experiment? The obvious experiment was to measure speed of light in different frames and in different directions, and noting whether there is a unique ether frame with respect to which the speed of light is c. So by this time, people were trying to find out experiments which will verify the existence of ether. It was A. Michelson who invented the interferometer and performed some experiments on the experiment. In 1881, he did first experiment, and later in 1887, he performed the experiment with Edward Morley. This shows the paper on which was based on this experiment. For his invention of interferometer and other optical experiments, Sir Albert Michelson was awarded the Nobel Prize in 1907. So what was the experiment about? The experiment was an attempt to locate the absolute frame of reference which was attached to ether, so-called ether. So they were trying to prove the existence of ether by measuring the speed of light in different directions as it moves through the medium. So what they did was they tried to basically measure the velocity of light in two perpendicular directions as the earth moves through the ether with a certain velocity. So imagine you have earth and a person standing on this earth. He sends out two perpendicular waves. Now this entire thing is moving through the ether. Say that the ether is moving towards the right with velocity. Earth is moving through ether with a velocity v. So the aim was to find out how will the velocity of light be measured when the earth is moving through this so-called ether with some velocity v. Before this, we knew that the Galilean transformation always mentions that the velocity will depend upon the relative motion of the source and the observer. This is the experimental arrangement. I will not go into details about the experiment because I think there is a session on the Michelson-Morley experiment. So you have a source and then there is a beam splitter, which is a semi-transparent mirror. So this mirror is going to split this light into two perpendicular portions. So this light which goes here hits the mirror, and this light which goes here hits the mirror. They come back, they interfere, and they show some interference pattern, which is detected with a detector which is placed here. Now, if ether is fixed and the earth is moving through ether in different directions, then there will should be some change in the interference pattern which was observed in the detector. This is a massive stone slab structure on which they had mounted their interferometer for stability. And the entire structure was actually floated on mercury so that they could move this through different angles. The main crux of the experiment is to conduct the experiment in two perpendicular directions. One, when the mirror is M1 is in this position and when the mirror is in this position. So this experiment was done various times in various seasons, and every time they thought of finding what is the difference in the fringe pattern. So you can see from this animation that since the earth is moving through ether, the light beams which move, by the time this mirror also has moved through a certain distance, Michelson and Morley calculated the fringe shift which is expected, and they conducted the experiment at 90 degree and 0 degree, and the fringe shift which was expected was 0.37, and after calculations and observations, they could not detect the fringe shift. So basically, they failed to detect the expected fringe shift. So, meaning they got a null result to what they were expecting. Now, when will you get a fringe shift? You will get a fringe shift if either the path lengths are different or if the speed is different in different directions. Now, Michelson and Morley made sure that the two path lengths, that is the distance from the beam splitter to the two mirrors, are exactly same. So they were expecting that if light travels with different speeds in different directions, there should be a fringe shift. And unfortunately, they didn't get the fringe shift. Question arises, whether this experiment is reliable and valid? Yes. So as I told, the conclusion can be either the earth is stationary, it is not moving through ether at all, or the ether doesn't exist. But we all know that earth is moving through space. So only conclusion which people could gather at that time was, at least for now, ether doesn't exist, or there is no experiment which helps in proving that there is something called as ether. So the interpretation made at that time was speed of light is same for all directions in every inertial plane. The null result was a blow to ether hypothesis. And this experiment actually was repeated over a period of some 50 more years after that also, and now it is confirmed that ether doesn't exist. But still, the scientific community was not very ready to accept it, because getting to accept something, an idea which is quite different, is very difficult. So many attempts were made to preserve the concept of preferred ether frame of reference. Some of these experiments were like Lorentz-Fitzgerald contraction hypothesis, ether drag hypothesis. Then they thought that when this failed to explain the existence of ether drag hypothesis failed to determine the presence of ether, they thought that there is something wrong with electrodynamics. But then experiments showed that, experimental data in all the three cases showed that this electrodynamics, there is no need to modify. And the only conclusion which we could gather from here is that ether does not exist. So speed is independent of observer's motion and independent of velocity of source. This was actually a great blow to Michelson also, because he was actually very, he was expecting to see some fringe shift, but which he couldn't see. And obviously, these results contradicts our Galilean relativity, because Galilean theory says that there is the speed of light will depend upon the relative motion of the source and the observer. So there was a need to change this thinking of Galilean relativity. So something new has to be done. And the first thing was to modify the Galilean transformation. And this leads us to the foundation of special theory of relativity. The Galilean transformation was replaced by Lorentz transformation. And this great gentleman, Einstein, in his 1905 paper on the special theory of relativity, provided a revolutionary explanation for the Michelson-Morley's null result. And this was 8 years after the Michelson-Morley's experiment was conducted. Even though he had not mentioned specifically Michelson-Morley experiment in his 1905 paper, but he had subsequently mentioned his knowledge about the Michelson-Morley experiment in later papers. So there is actually a lot of controversy whether Einstein actually knew about the Michelson-Morley experiment when he wrote these papers, or whether he did it independently, because in 1905 paper, he had actually not given credit to Michelson-Morley, but then there were a lot of historians who went into and checked the mail letters which were written by Einstein. And now we know that this experiment indeed had a great influence on Einstein and his ideas about the relativity. So Einstein introduced the concept of space and time, where you have space and time which are interconnected. Speed of light is same for all observers regardless of the motion. And the foundation of special theory of relativity is based on two postulates. That is, the laws of physics are same in all inertial systems, and the speed of light in free space has the same value in all inertial frames. So Michelson-Morley experiment was indeed a game-changing experiment because of not what it did, you can say because of what it didn't do. That is, it didn't get the expected interference fringe shift. So what is the legacy which Michelson-Morley experiment has led? It has revealed the cracks in our understanding of physics at that time. Because Michelson-Morley experiment failed, people thought they have to think about new theories. Its failure to detect the ether provided experimental evidence that challenged the notions of space and time, which was prevalent at that time. And that's the reason why Einstein's idea also got approved. And it laid the groundwork for Einstein's special theory of relativity, which introduced a new framework for understanding the fundamental principles of the universe. It will not be wrong to say that it has revolutionized our understanding of space, time, and the relationship between them. So it is a landmark experiment, and to do a precise experiment with those facilities at that time is really commendable. So to conclude, the Michelson-Morley experiment is important because it challenged existing ideas about our nature of light and space, and eventually led to the development of special theory of relativity. And this theory has revolutionized our understanding of the fundamental principles governing the universe and has profound impact on the field of physics and numerous technological applications. Hence, even though it was an experiment which didn't give us the expected results, it was considered to be a failed experiment, but it is now considered as the most famous failed experiment because it has led to new dimensions in our understanding of physics, particularly space and time. The references for the figures. Thank you for your kind attention. If you have any comments, I'll be free to take. Thank you. I try to keep it very simple, without any mathematics, just to give you a brief idea of how the story unfolded. Yeah, am I audible?
Yeah, ma'am, can you please switch on your video?
Oh, I was trying to save the bandwidth. Yeah, I'll sure do that. I think something is wrong with the camera.
Okay, don't worry.
Yes,
I
sir.
just wanted to ask you, are you a member of IEPT?
Yes, sir. Yes.
But are you receiving our emails or not?
I'm receiving still the booklets.
Okay, actually, we don't have your email and your mobile number with us.
Okay.
And once we get that, we will update it. This is the
And now
first.
the actually organizers may be having it, or I
Yeah,
can send it to you by. Yeah.
Yes, I will ask from them.
Sure.
But you can send to me also directly if you feel like.
Yeah.
On my mobile, I'll just write my phone number, okay?
Yes, sir.
The chat. Chat is my notes here. Okay. Can you see the notes?
Not able to see.
Let me just.
Yeah, I can. I can see
this. This is my mobile number.
But I can't see your number. Nothing. I can just see notes, but nothing written.
And then there must be chat somewhere here. I'm not able to see chat immediately. I can see only notes here. All right, but my number
Can
is.
you see my hello?
Hello. I can't see your hello as such. This is there is a something called chat here. Notes I can see, but I can't see the chat.
There is no chat option, I think, in this.
So my number is 98050-76451, ma'am.
Sir, once again, 98?
98050.
Yeah.
76 451.
Okay, sir.
Right. Okay. I really liked your lecture very much.
Thank you so much.
Very simple, to the point, and you highlighted that sometimes when we plan big experiments, we expect some results.
Yes.
Kind of a hypothesis which we have in our mind. And if it doesn't happen, then that may stir many people around to see why that is not there.
I always tell my students, if failed experiments or if you don't get the result, don't get disheartened.
Yes.
It may be the beginning of some new ideas.
And there was one very interesting feature in this.
Huh?
That to explain the null result, people thought of a correction of square root of 1 minus v square upon c square.
Yes.
Which ultimately, became very prominent when we were seeing special theory of relativity. And we talked about variation of mass, which people never expected. Then we talked about length contraction. It was sitting there, this correction factor. Then in time dilation, it was also sitting there. And it required a person of the caliber of Albert Einstein to really see which many people were trying, but they were not really coming to the crux of the matter. Only he could postulate those postulates of theory of special relativity, through which they could see everything else. I think you are a wonderful speaker, ma'am. I must say that.
Thank you so much. It means a great to me, sir.
You can be an asset to IEPT as a communicator of physics. Congratulations.
Thank you so much, sir.
This is
My
my
pleasure.
discovery of attending this lecture.
Thank you so much.
Yes. Okay, I really enjoyed it. Thank you.
ಶೇರ್ ಮಾಡ್ಬೇಕು ಇಲ್ಲಿದೆ ಶೇರ್ ಕೊಡಿ PPT ಕೊಡ್ಬೇಕಲ್ಲ ನೋಡಿ ಇದು ಶೇರ್ ಮಾಡ್ಬೇಕು ಶೇರ್ Hello. I will share my this one. One second. Hold on. Share ಮಾಡಲಾಗಪ್ಪ one second. I have to share this one.
Send this to mail.
Which mail?
Mail.
Oh, is it? Mail, Gmail. Gmail.
Just a second.
ಅಲ್ಲ ವೆಬೆಕ್ಸ್ ಇದು
Minimize. Stop sharing. Minimize.
ಎಲ್ಲೇನು
Hello.
Hello.
Yeah, sir. Good afternoon.
Good afternoon. I am trying. There is some problem. In 2 minutes, I will be joining.
Okay, you rejoin, sir. Meanwhile, who is the next speaker, please? SW Anwane, sir. Are you there, sir? Hello.
Yes, sir. Yes, sir. I'm there.
You, sir. Please, you start. You start.
Yes, sir. Definitely, sir.
Yeah, you start, sir. Thank you.
ಯಾಕೆಂದ್ರೆ ಒಂದು ಗ್ಯಾಪ್ ಇರುತ್ತೆ ನಮ್ಮ ಸಬ್ಜೆಕ್ಟ್.
Is my screen visible here? Hello. Am Am I audible?
Yes, sir.
Can you see my screen?
Yes, it is visible.
Okay, sir. Thank you. Good afternoon.
Good afternoon. Very good. Wonderful. I enjoyed this video earlier
Yes,
also.
sir.
Great.
Yes, sir. A very good afternoon to one and all present here, dignitaries and invited speakers of the second national workshop on gravitational waves organized by Jaipur National University. Office bearers of IIPT, I humbly recognize the presence of Professor P.K. Ahluwalia, sir, President of IIPT, and distinguished physics teachers and my dear students. I welcome you all to this today's session where we embark on an exciting journey through the intricacies of our Sun-Earth system. Our primary objective of this session is to delve deep into the realm of astrodynamics as we endeavor to calculate one of the most fascinating and the crucial points in the cosmic dance, the Lagrange point L1. The Sun-Earth system, a celestial ballet, has captivated human curiosity for centuries, presents a captivating playground for celestial mechanics. As we explore this intricate dance between our radiant sun and our resilient earth, we will unearth the delicate balance of the gravitational force, orbital dynamics, cosmic harmonics that governs their interactions. The Lagrange points, first discovered by the brilliant French mathematician Joseph Louis Lagrange in the 18th century, represents a stable equilibrium points, a set of stable equilibrium points within the gravitational interplay. Our focal point L1 is the place where the gravitational forces of Earth and Sun conspire to create an equilibrium that allowing the objects to maintain their relative position with respect to our planet. Throughout this talk, we'll not only unveil the theoretical unpinning of the Lagrange point L1, but we'll embark on the fascinating journey of the mathematical calculations striving to pinpoint the celestial sweet spot. We'll examine the significance of L1 in the space exploration, the satellite positioning, and even the space mission like James Webb Space Telescope. The successful beginning of the Aditya L1 mission has created a mass awareness of the vantage point, the Lagrange point L1. The Aditya L1 mission, born with a vision and dedication of India's space agency, the Indian Space Research Organization, ISRO, represents a remarkable step towards our quest to comprehend the enigmatic sun named after the radiant Hindu Daitya, Aditya. This mission is set to venture closer to the sun than any previous Indian space mission. Positioned at L1 Lagrange point, which provides an ideal vantage point, Aditya L1 aims to study sun with unprecedented precision and depth. Aditya L1 is a satellite dedicated to the comprehensive study of the sun. It has 7 distinct payloads all developed indigenously. 5 by ISRO and 2 by Indian academic institutions in collaboration with ISRO. The sun is the star at the center of the solar system. It has a massive hot ball of plasma inflated and heated by nuclear fusion reactions at its core. Part of its internal energy is emitted from the sun's surface as light, ultraviolet, and infrared radiations, providing most of the energy for life on Earth. The sun's radius is about 695,000 kilometers. Its mass is about 330,000 times than the mass of Earth and is comprising about 99.86% of its total mass of the solar system. Earth's rotation or Earth's spin is the rotation about the planet. Earth rounds its own axis as well as changes the orientation of the rotational axis in space. Earth rotates eastward in prograde motion as viewed from the northern polar star Polaris. Earth rotates in about 24 hours with respect to sun, but once every 23 hours, 56 minutes and 4 seconds with respect to the other distant star. Earth's rotation is slowing slightly with time. Thus, a day was shorter in the past. This is due to the tidal effects the moon has on Earth's rotation. There are three collinear Lagrange points. I think in this slide you can see the three Lagrange points. I want a pointer. So L1, L2, and L3, they are collinear, were discovered by the Swiss mathematician Euler in 1750. Decade before, Italian-born Lagrange discovered the remaining. I think I have covered this rotation of Earth. This is a wonderful contour plot which has been developed. Potential derived from the Coriolis force. Now, for estimation of Lagrange point in the Sun-Earth system, one has to understand the centripetal force that everyone has taken care of this in our school times only. Here, for estimating the Lagrange point, we have to understand the basic formula for velocity, that is distance upon time. When the Earth is orbiting in the radius r, it takes 2 pi r distance in 365 days, that is period. So 2 pi r is the circumference of the orbital path divided by time. So here we have to account for two forces. The force on Earth due to Sun. The gravitational force supplies the necessary centripetal force for circulation. So here on right hand side, we have mv square upon r. So the mass concerned is mass of Earth. Velocity concerned is velocity of Earth divided by distance r, which is the radius of the orbit. This mass of Earth and mass of Sun. Gravitational constant g times me into ms upon r square. So here we can eliminate mass of Earth. It is identical on both sides. So here I would like to show that this mass of Earth can be eliminated from both the sides, and we are left with the equation g into mass of Sun divided by r square, that is equal to 1 by r. So this r in the denominator we have, and we have ve square. This is to be substituted from this formula. Actually this is ve, so 4 pi square r square divided by t square. Now g times ms upon r square is equal to 4 pi r square. This 1 r is cancelled with one of the r in the numerator. So 4 pi square r upon t square we have. This is the important equation. I am going to pin that on the next slide so that you can readily understand the things, how it is going on. So this is that equation. Now we want to calculate the force on satellite. So force on satellite we want to calculate because of Sun and Earth. So here there are two forces that we have to account for. The gravitational force of attraction F is equal to G into m1 m2 upon r square. So here we have to consider mass of Sun into mass of satellite divided by the distance between two. Actually that diagram here you can observe that this is the point where L1 is located and r is the radius that is starting from center of Sun to center of Earth, and L1 distance I'm calling this between Earth and this point. So when we want to account for distance between L1 and Sun, it will be R minus L1. So R minus L1 is this distance where the satellite is going to orbit around Sun along with Earth. So this is the trajectory followed by the satellite here. Now the gravitational force is G into M1 M2 upon R square. The distance here I wanted to highlight that it is R minus L1 square minus G times ME, mass of Earth, into mass of satellite divided by the distance between Earth and the satellite that I'm talking about. I'm talking about this distance now. So that is L1. That is equal to mv square upon r, same centripetal mass, centripetal force formula. So here the rotating object is satellite, so mass of satellite multiplied by v square, that is velocity of satellite square, divided by the distance between two, that is r minus L1, that I have already explained to you. So here I have modified this formula for v satellite. The distance is 2 pi r, and this time the orbit is r minus L1. So I'm talking about this r minus L1 orbit divided by period. So v sat square will be 4 pi square r minus L1 square divided by t square. So in the next step, I'm going to replace this v sat. Now here we have what we can cancel out here is this small m here, and small, we can divide the entire equation by small m, that is mass of satellite, and we are left with G into mass of Sun divided by the distance between satellite and Sun, that is r minus L1 square minus G me upon L1 square, that is equal to 1 upon r minus L1. This very denominator I have separated out, and we are left with v sat square. So we can plug in that value
Hello?
Hello, sir, can you hear me?
Yeah.
I'm again sharing my screen. There was some interruption.
Okay, I think. Anwane,
Yes, sir.
you are continuing?
Yes, sir. I have again joined.
Yeah. Go.
Sir, yes.
So we were somewhere with the equations. So we were here, I guess. Now, here I think we have eliminated this m, and we have to substitute this v sat square from this very equation, and then we are left with this equation, this 1 upon r minus L1 we have here this way, and 4 pi square r minus L1 whole square divided by t square. Now, we are taking this quantity to numerator r minus L1 to the power minus 2 we are taking, and we are taking 1 by r square this way, and we are writing it as 1 minus L1 upon r to the power minus 2, and then we are making binomial expansion for that 1 by r square into 1 plus 2L1 upon r. This sort of approximation we are making for the condition that L1 upon r, that is the distance of the satellite from Earth to the distance of Sun from Earth. This is a very small quantity. So for this we have made this approximation by binomials theorem, and we are going to substitute this value for this binomial expansion, and the rest things are as it is, except that we have cancelled 1 here with this one, and we have taken r common here, and inside we are left with 1 minus L1 upon r. So this is the little adjustment that we have done. Now here we are left with g ms upon r square into 1 plus 2 L1 upon r minus g me upon L1 square, that is equal to 4 pi r upon t square. So this quantity in the next equation I have with another color because I wanted to substitute it. I want to replace this by this g into mass of sun divided by r square. So here we want to replace this by g ms upon r square. On the next slide we are going to do that. So here we have substituted this value. Now we have this equation again for our consideration, where g is common, so gravitational constant can be eliminated from our equation, and ms upon r square into 1 minus twice L1 r minus me upon L1 square, that is equal to ms upon r square 1 minus L1 r. Now this can be further simplified as ms upon r square times this 1, and here we have ms upon r square. We can subtract the same quantity on both sides, and then we are left with this twice L1 upon r, and we are bringing this to left hand side. It will be thrice L1 upon r times ms upon r square minus me upon L1 square, that is equal to 0. So we can make a simple equation, and now our aim is to find L1 on left hand side. So this L1 square into this L1, we are taking it on left hand side. So L1 to the power 3, that is equal to ME upon thrice ms into r cube. And if we take cube root of this, it will be L1, that is equal to r into cube root of me upon thrice ms. So that is the equation we were striving for. So I'm just rolling through what I have written. Same equation we are doing. So this L1 is equal to r times cube root of this. So here we want to substitute the distance between Earth and Sun, that is 1.5091 into 10 power 11 meters. Then mass of Sun about 2 into 10 power 30, and mass of Earth is about 6 into 10 power 24. So we can plug in these values, and here you can see that this 6 with 3 into 2, 6 vanishes, and inside the square root cube root we have 10 to the power minus 6. So 10 to the power 24 minus 30, it will be 10 power minus 6. So cube root of that 10 to the power minus 6, cube root of that will be 10 to the power minus 2. So here 1.5 into 10 power 11 to be multiplied by 10 power minus 2, that offers us 1.5 into 10 power 9 meters. So that is 10 power 9 meters means 1 million kilometers. So 150 million kilometers is the total distance r, and here this is the 1% distance that we have. Now we are going to the last slide of my presentation, wherein you can see the Lagrange points and you can identify the position of Earth and L1. And here you can very well locate that here moon is revolving around Earth and L1 point is far, and here this makes a clear vantage point to observe sun. So here I have one small animation that the satellite is reaching to that point, and after orbiting from here, so I want a pointer here, laser pointer. So here the satellite has escaped from the Earth's gravitational field, making more and more elliptical path, and then it has taken its journey, and now it is orbiting around the L1 point with minimum energy, giving us a clear glance of sun. So this is all about my presentation. If any student has any question, I would like to answer. Is any student having any question? So I'm done with my presentation. If anyone has any question, we can have a discussion.
Thank you very much. If I'm so
There is some echo effect. I am unable to understand what is being said.
Hello. Hello. When Hello. Yeah, thank you very much, sir. A very nice presentation. Now our students are able to know why we have chosen L1. So next is Dr. Venkesh.
Yes, sir. I'm
Yeah,
ready.
yeah. You start, sir.
Shall I start?
Sure.
Good afternoon to you all. Hello, can you hear me? Hello,
Yes, sir.
shall I start?
Yes.
Very good. ಮುಂದೆ ಹೋಗೋದು ತಾನೆ? ಇಲ್ಲಿ ಮಾಡಿದ್ರೆ okay. The velocity of light in vacuum is of fundamental importance in physics. It is a single limiting velocity in the universe and the upper bound to the propagation of all signals and speeds of material particles, and it is used in the standardizing of the meter. It is used to measure large distances accurately, and also it appears in the fine structure constant 1 by 133 in the form E squared by 4 pi epsilon naught h cross c. Now, Michelson and Morley experiment is one such experiment where people, particularly Michelson and Morley, were very keen to measure the velocity of light very accurately. In fact, you youngsters should know that Michelson and Morley nearly worked on this experiment for 40 years, from 1887 to 1927. So that is the reason why this particular experiment, in fact, Michelson was the first American physicist to get the Nobel Prize for his experiment on the measurement of the velocity of light. Michelson actually measured the velocity of light in the beginning. Then he used the same apparatus to measure the relative velocity between the Earth and the omnipresent ether. The Albert A. Michelson lived between 1852 and 1931, a physicist, an American physicist, joined by Edward Morley, who was senior to him, but a chemistry teacher. In fact, he was a chemist, and he lived between 1838 and 1923. As I mentioned, these are the reasons why velocity of light is very important for us. And there are very many methods of determining the velocity of light. I have only highlighted a few. The first earlier experimental determinations were by Romer, by observing the eclipsing of the satellites of Jupiter, later by Bradley, by observing what is called the aberration, the difference between the true direction and the apparent direction of a star. Apart from this, there are a number of terrestrial experiments. I am mentioning 3 here because the experiments which came after Michelson are not discussed here. The first one is the Fusier's toothed wheel method, the Foucault rotating mirror method, and the Michelson's octagonal mirror itself, then which was modified as the Michelson's interferometer. Now, in the two experiments of Fusier Foucault, the idea was to make a light signal travel from a particular source to a distant mirror, get it reflected back, and the time taken between these two distances between the light traveling these two distances was measured, and the distances were known, and the velocity was calculated. In both the methods, Fizeau and Foucault, the light was traveling in a particular direction and retracing the path. In the Michelson's octagonal mirror method, also the same procedure was there. But before I go to the actual, in fact, I can just go to this one. The experiment of Michelson-Morley was performed in Cleveland in 1887 to detect the existence of luminiferous ether. The problems it posed led indirectly to Einstein's special theory of relativity. As I mentioned here, in all terrestrial methods of determining the velocity of light, the light comes back along the same path again, so that the velocity of the Earth with respect to the ether would alter the time of the double passage by a quantity depending on the square of the ratios of the Earth's velocity to that of light. That is v squared by c squared, where v is the velocity of the Earth and c is the velocity of light. And this difference is quite too small to be observed. This is the observation in the Fizeau and Foucault's method. And we know, in fact, in the earlier talk also, Madam has mentioned this. According to wave theory of light or wave theory of radiation, a medium is necessary for the propagation of all waves. Light was imagined to be traveling in all-pervading, omnipresent, and hypothetical medium called ether, which is also called the luminiferous ether. It was all-pervading and omnipresent. In fact, in the words of Einstein, no doors are closed for ether. Ether is present everywhere. So, if all the celestial bodies, including the Earth, must be moving in the sea of ether, there should be a relative velocity between the two bodies, that is the Earth and the ether. And Michelson and Morley's experiment was designed to measure this relative motion of the Earth with respect to ether. Many people call Michelson-Morley experiment as a failure experiment. It is not a failed experiment actually. It is an experiment which did not give the expected results. It was a null result experiment, not a failed experiment. Experiment did not fail, but the result was not what was expected. And the Michelson's plan was remarkably very simple. He dispatched two mutually perpendicular directions. As I mentioned in the earlier two cases, the light traveled in the same direction before and after reflection. But in the Michelson's plan, the light signals were traveling in two different perpendicular directions, but equal distances. And they are reflected both back to a common point and produce the interference pattern and measure the difference, if any, there was between the two arrival times. That is, the travel time of the light signal from A to the fixed mirror M1, let us say, and from the same mirror to another movable mirror in the perpendicular direction, and these two distances of the mirrors from the point where the beam splits into two parts were exactly at the same distance. So if there was a difference in the velocity of the traveling of these signals in two different directions, there would be a path difference and hence a phase difference, which produces a shift in the fringe pattern, which is obtained due to the interference of these two beams. And this is what Michelson and Morley were interested in. So they sent a signal from a source and onto a semi-polished mirror. One beam was reflected to a mirror in the perpendicular direction and the other along the direction of the Earth's motion. Assume that the direction A to the fixed mirror is along the direction of the Earth's motion and the direction B is along the perpendicular direction. Now, if we make the distances of the two mirrors exactly the same, and in the case of the signal going from the split signal going from along the A direction to the fixed mirror and back is affected by the velocity of the Earth. So in one direction, the velocity of the Earth adds to this velocity. In the opposite direction, the reverse direction, it opposes. Therefore, there is a difference in time between the arrival of the signal. Similarly, the light going from this split mirror to the other mirror, which is almost exact, it is exactly at the same distance from the zigzag mirror, is traveling back. And in this direction, the velocity of the Earth will not affect the travel of this signal. And both these signals are now obtained as the interference pattern on the screen. Now, this was the experiment of Michelson and Morley. And if you simply, of course, consider a brief theory of this one, the time taken for the light to travel along the direction in which the Earth is moving, it is L by V plus V in one positive direction, and in the reverse direction, it is L by C minus V. And in the perpendicular direction, it is the same in both the cases. Therefore, it is 2L by C into 1 plus V squared by 2C squared. I am not going into the algebra of this one. But if you calculate the time difference between the two, ignoring the higher powers of V squared by C squared, we get approximately the value as 2L by C into V squared by 2C squared, which gives you LV squared by C cubed. This is the time difference. And if you convert this into path difference, it is C into delta T, which is LV squared by C squared. Now, a path difference of lambda corresponds to a shift in one fringe. Hence, for a path difference of delta x, the fringe shift is expected to be LV squared by lambda C squared fringes. Now, this is the theory of the experiment. And Michelson and Morley actually designed this experiment such that the fringe shift which was expected from this calculation was of the order of 0.4 angstrom units. But the design of the apparatus was such that it could measure the fringe shift, which is 10 times smaller than this one, smaller than the expected difference. However, they were unable to measure this difference. Therefore, the experiment was a null result experiment. And Michelson and Morley had originally planned to make observations during each month throughout the entire year, so that every stage of Earth's motion through space would be included in the experiment. In this way, any fortuitous cancellation of the Earth's motion around the Sun by the velocity of the entire solar system through space would be revealed. And they give the final result of their experiment in July 1887. Now, in 1899, Henri Poincaré of France, a physicist, proposed that the Michelson-Morley experiment be generalized, that the absolute motion in principle not detectable by laboratory experiments of any kind. The two important conclusions of the Michelson-Morley experiment are: one, there is no ether, or even if ether is there, it will not affect the velocity of light. In other words, velocity of light is independent of the source or the observer. And this idea was used by Einstein in proposing his special theory of relativity. Next one. Now, one or two points I would like to mention. Albert Einstein in 1905 proposed the special theory of relativity in his paper on the electrodynamics of moving bodies. Though Einstein's special theory of relativity do not refer to the results of the Michelson-Morley experiment, Einstein later, in the birth centenary of Michelson, acknowledges that the results of the Michelson-Morley experiment is very important for my special theory of relativity. Now, the Michelson-Morley experiment was explained by different methods, in fact, by different observers, Lorentz explained this as the ether drag or Lorentz contraction. In fact, I'm not going into the details of that. In the direction of motion, the length gets contracted, and therefore there is no difference between the time intervals of the two signals reflected from the two mirrors reaching the observer. Now that is one observation. And the second observation, second explanation was the ether is dragged along with the earth, therefore there is no relative motion. Now, of course, this leads to other complications, which I am not going to mention at this point. Now, on the basis of but Einstein actually came to the conclusion of the postulates of the special theory of relativity on two important postulates. So he said that all laws of physics must have the same form in all inertial frames. In other words, the laws of physics are covariant. Now, what do we mean by a law of physics? A law of physics is nothing but the codification of experimental results. And therefore, this should not depend on the choice of the coordinate system. If we perform an experiment in Bangalore, in Jaipur, in London or New York, the same result should yield. That is what the principle of covariance is. So all laws of physics must have the same form in all inertial frames. He called them as the laws of physics are covariant. And also, he said that the velocity of light is the same for all observers, irrespective of the motion, relative motion. That is, the velocity of light is invariant. So the two postulates can be simply stated like this. Laws of physics are covariant, velocity of light is an invariant. These are the two simple laws. And as a consequence of the special theory of relativity, we have a number of the interesting results. The length contraction, that is, if you think of an object which is moving at a very fast speed, comparable to the speed of light, the length of the object gets contracted. This is known as length contraction. If I call L as the length of the object in motion, and L naught as the length of the object at rest, and if the object is moving with a velocity v, then L will be equal to L naught into root of 1 minus v square by c square. This is the amount of contraction that happens. If you apply this to the case of the Michelson-Morley experiment, the null result is satisfactorily explained. Then the time dilation. The time, according to Newton, time is absolute. That is, time measured by different observers will be the same. But according to the special theory of relativity, the time measured depends on the state of the observer. If you measure the time by a clock which is at rest and by a clock which is in motion relative to an observer, then the two intervals are not the same. In other words, the time interval measured in a frame in which the clock is moving appears to be elongated. In other words, moving clocks go slow. That means time appears to dilate in moving the clocks, and the length appears to contract in the moving frames. And in addition to this, a very interesting result is the velocity addition. Now, if you think of normal velocities in Newtonian mechanics or in Galilean transformations add up simply. If V1 and V2 are the velocities in the same direction of two objects moving in the same direction or in the opposite direction, then the relative velocity is V1 plus or minus V2. But in the special theory of relativity, we have to have a new velocity addition theorem. It is not V1 plus V2, it is V1 plus or minus V2 by 1 plus or minus V by C squared. That is the relative velocity, a new addition theorem. And then, of course, the famous Einstein's mass energy relation, E equals mc squared. So here, I would like to mention two important points. The theory of relativity challenges common sense. Now, what do we mean by the theory of relativity challenges common sense? This is C plus D is not equal to 2C. C plus C is still C. It is against common sense, right? And then Einstein himself gives this one. Challenging the common sense means people will ask, what is common sense now? Now, please note the definition of common sense. Einstein himself has given. It is that layer of prejudices that we have developed before we are 16. That is, you have been taught in your classes that 1 plus 1 is 2, 1 plus 1 is 2. Now, this is for a particular base 10. If you change the base, 1 plus 1 is not equal to 2. This is what I say challenges common sense. So, this velocity addition is challenging the common sense. I will give a simple example and then conclude my talk. See, if you are imagining a thief and a policeman, let us take this case. A policeman and a thief. The thief sees the policeman starts running at 5 kilometers per hour. The policeman also runs at the same speed. He will never be able to catch. On the other hand, the thief runs at 5 kilometers, the policeman runs at 7 kilometers per hour, and the relative velocity is 2 kilometers. After some time, the policeman will catch him. On the other hand, the thief runs at 5 kilometers, the policeman runs at the same 5 kilometers in the opposite direction, which normally happens in the daily life. After seeing the thief, the policeman will go in the opposite direction. So in this case, there is the relative velocity is not v plus v. It is not v plus v. It is the v minus v 0, but it is not the same in the case of special theory of relativity. It is different. So this is a new velocity addition method. And these are the important consequences of the special theory of relativity. And the most important result of the special theory of relativity is the conversion of mass into energy, E equals mc square. So in 1952, on the occasion of the birth centenary of Michelson, Einstein acknowledged his debt to Michelson and Morley. The influence of the crucial Michelson-Morley experiment upon my own efforts has been rather indirect. I learned of it through Lorentz' decisive investigation of the electrodynamics of the moving bodies, which I was acquainted before developing the special theory of relativity. This is the importance of the Michelson-Morley experiment. Thank you. Thank you, sir. Any questions?
Any question? Thank you. Hello.
क्या कह रहा है वो विमल? आपकी बात हुई है क्या? Hello.
Hello.
Yeah, I think, sir, we have to stop here because
Yeah,
now.
that's fine. I have stopped that.
Yeah. Okay, sir. Thank you very much. Now, Dr. Vivek Bide is here. Hello.
Hello.
Yeah, thank you, sir. Dr. Bide, am I audible?
Yes, sir. Yes, sir.
So, could you please conclude your talk within 5-6 minutes?
I will
Yeah,
try
okay,
to my
sir.
best.
Okay, sir, please. You start, please. Hello. Yeah, Dr. Bide.
Yeah, is it visible?
Yes,
whether
yes,
the
it is
paper is
visible. Yeah, it is visible.
Okay, okay, okay. Now, first of all, thank you for giving me such opportunity. And sorry, but I will have to make some hurry. And the topic is waves, interference, and interferometer. Now, if we think about the overall schedule of this session, I will have to conclude within 5 to 6 minutes. It is a bit difficult, but I will try to my best. And I will emphasize on the waves and interference because the Michelson's interferometer is already covered by the dignitaries. Now, what is wave? Basically, whenever the source produces some disturbance in the medium, depending on the elastic property and inertial property of the medium continuity, there is a transfer of energy through the medium from one point to other in the direction of propagation of wave depending on the property
Hello.
of the medium, either in the form of, hello sir.
Yeah, Dr. Bhide, your screen is not visible. If you could speak only for 2-3 minutes, it will be better.
Is it visible now?
Yes, it is visible, but I don't think we'll be able to finish it within because at 3:30 the buses will ply. So
the buses will fly at 3:30.
Yeah.
Sir, can I request one thing? I will record my topic based on wave interference and interferometer completely.
Yeah. Please share that. Later on, we will share with the students.
Share with the audience.
Yeah, that will be better.
Okay, thank you, sir.
Okay,
Thank you,
sir. Thank you. So with this, we thank to Dr. Vivek Bhide and other speakers of this seminar. Sir Nitin sir and Lokesh ji, you please conclude now. Lokesh ji.
Yes, sir.
अब आप लोग conclude कर दीजिए इसको, है ना? Thank you very much. Thank you, students. Bye bye.
ऑनलाइन क्विज थोड़ा सा